Welcome to the next part of lecture. Now I will introduce Hilbert transform. Before that, I want to introduce one important result. These results are important independently also. One is that let me first define a signum function, Sgn of t. So signum function looks like this in this figure. It is 1 for t greater than or equal to 0, minus 1 for t less than 0. We also note that if we add 1 to the signum function and divide by 2, so it will become half 1 plus 1 for t greater than or equal to 0 and half 1 minus 1 t less than 0. That is 1 half of 1 plus signum becomes 1 for t greater than 0 and 0 for t less than 0. It becomes u of t. You can see from this figure, if to this figure we add 1, 1 is simply this. What will you get? You will get, so this part gets cancelled with this part and you will get 2 here, right? Now if you divide this by 2, you will get this function. This is u of t. Okay, so we have an important relationship, half 1 plus signum is equal to unit step function, or signum is equal to 2 times u of t minus 1. Now if you take Fourier transform, so Fourier transform of signum function is 2 times Fourier transform of unit step function. And what is the Fourier transform of 1? It is 2 pi delta omega. You have done this already. So this is 2 pi delta omega plus 1 over j omega minus 2 pi delta omega. This and this goes cancels. So Fourier transform of signum function is 2 divided by j omega. Okay, so this is one result. Let me, for sake of convenience, let me say that g of t is a signum function and its Fourier transform capital G of omega is 2 over j omega. So I can write g of t g of omega. There is one important result in Fourier transform. You might have done the same result or the same thing in Laplace transform. That's called duality property. So there are several dualities. There's a time frequency duality. So this particular duality property, it talks about if you replace frequency by time and time by frequency, so then what will be the Fourier transform of that function? Suppose you have a function g of whose Fourier transform is capital G of t, g of omega. So what it says that if you replace, now in capital G you had g of omega, if you replace this omega by t, okay, what will be its Fourier transform? So the result says that to find the Fourier transform of this function, you need to do this thing 2 pi, then in g of t you replace this t by minus omega. So as an example, for example, you know that e to the power minus at u of t, you know its Fourier transform, that is 1 plus a plus j omega. Okay, now if you want a Fourier transform of 1 over a plus jt, what should you do? Just 2 pi, okay, e to the power, now here will be a omega u of minus omega. So you have to reverse. Okay, it says that if you have in Fourier transform, if you replace time by frequency, frequency by time, what will be the Fourier transform? 2 pi times, in the time function replace time with the frequency minus omega. Now how is it helpful? It will be helpful for us. Right now we will apply it to the signum function. So you have a signum function, okay, whose Fourier transform is 2 over j omega. Now if I replace this 2 over j omega by t, so this is now our g of t. What will be its Fourier transform? It says that you have to do 2 pi signum of minus omega. Okay, that is what this result says. Or in other words, 1 over Now if I will do this 1 over pi t, its Fourier transform pair is j signum of omega, because signum of minus omega is same as signum of omega. Okay. Sorry, I think signum is odd function. Let me just, yeah, see, signum is an odd function, because if you replace, if you do signum of minus t, so that will become 1 minus t greater than equal to 0, and minus 1 when minus t will be greater than 0, less than 0. Okay, so this will become minus 1 for t greater than 0, and 1 for t less than equal to 0. Okay, so this is minus of signum of t. So signum is an odd function, so I should write here that 2 pi signum of minus will be minus signum of omega. Okay, so from this what we have got is 1 over pi t forms the Fourier transform pair with j signum of omega. Okay, in other words, Fourier transform of 1 over pi t is minus j signum of omega. Now hold on with this result, you will soon realize why we were doing all this. Now coming back to our discussion of time domain representation of single sideband signal. I repeat once more, suppose if this is the Fourier transform of so sorry, I want it to be symmetric. Suppose if this is m of omega, so upper sideband we call as m plus of omega, lower sideband we call as m minus of omega. Since m of t is the message signal, right, whose Fourier transform is m of omega, we want to find the corresponding time signals for m plus of omega, m minus of omega, right? So m plus of omega will have some m plus of t corresponding time signal. Similarly, m minus of omega will have some corresponding time signal m minus of t. We want to find it. So one thing is clear, that m plus of t plus m minus of t must be equal to m of t, right? Because they represent one part of the signal, correspond to one part of spectrum, so jointly they should represent the whole signal, message signal, right? That is one thing. Now see one thing, if I separately draw m plus of omega, now you recall yesterday's lecture in which I told that if Fourier transform is not symmetric, then the signal must be complex. Remember that? See this Fourier transform, it is not symmetric. Okay, note these points, they are not given easily in the books. They are scattered in several books which I am presenting to you. So it is not symmetric, so the corresponding time signal m1 of t has to be complex. There is no other way. Similarly, if you look at the lower sideband, m minus of omega alone, this also is not symmetric, so m minus of t has to be complex. But they are such complex numbers that their sum is equal to m of t, which is real, right? See, if you have a complex number z1 and you have another complex number z2, but they are such that when you add them up, you get a real number, some real number, suppose y. So this is real. So what type of complex numbers will they be, right? So they will be of the form a. If z1 is of the form a1 plus jb, then z2 has of the form a2 minus jb. The imaginary part should be equal. equal, so that a1 plus a2, the sum is real. Okay, but further you know that their sum here is m of t, so the only form of m plus of t and m minus of t has to be this m of t plus j times m h of t. I call as imaginary part. The reason for h will appear soon, why it is h. Similarly, m minus of t I can write as half m of t minus j times mh of t. Now in this form I have represented the positive part and the message signal corresponding to upper sideband spectrum and the message signal corresponding to lower sideband spectrum. You see it satisfies all the properties. M plus t plus m minus t is m of t. mh gets cancelled and both are complex. Hence it is justified that their Fourier transform is not symmetric. Okay. Now coming to m plus of omega first, which is the positive part of spectrum. How can we obtain that? Just multiply the spectrum with unit step function. Very nice. And you know that if I want to write unit step function in terms of Signum function, so that will be 1/2 of 1 plus Signum of omega. Okay, so it will be 1/2 of m of omega plus 1/2 of m of omega Signum of omega. So far so good. Now you look at m plus of t, that is half m of t plus j by 2 mh of t. Just go back here, this one. Okay, equation 1. Now we know that m plus of t has Fourier transform m of omega. Now component wise it means half m of t plus j over 2 mh of t has Fourier transform m of omega by 2 plus half m of omega Signum of omega, right? So it is clear that this half m of t has Fourier transform m of omega by 2. Hence jmh by 2 has Fourier transform half m of omega Signum omega. In other words, we can write that j mh of t has Fourier transform m of omega Signum of omega, or if I multiply j on the both sides, I will get mh of t as Fourier transform minus j m of omega Signum of omega. See, I have got the Fourier transform of mh of t, right? Okay, now I want to get a time function also of mh. This is the Fourier transform of mh of t. How can I get that? Now look at this. You know that m of omega has Fourier transform. It is a Fourier transform pair with m of t. You also know Signum of omega forms Fourier transform pair with. Okay, so I will go back to this result. Now this is what we needed. 1 over pi t forms Fourier transform pair with minus j Signum of omega. So I will write here minus j Signum of omega forms Fourier transform pair with 1 over pi t, right? And you know in Fourier transforms that if g1 of omega has Fourier transform pair with g1 of t, g2 of omega forms Fourier transform pair with g2 of t, then just a moment, then g1 of omega times g2 of omega will form Fourier transform pair with convolution of g1 of t with g2 of t. This is the basic result we know, right? So if your g1 of omega is m of omega, your g2 of omega is minus j signum of omega, and your m of t is g1 of t, your 1 by pi t is g2 of t. So what you can say, g1 of omega, g2 of omega forms Fourier transform pair with g1 of t convolution with g2 of t, which is equal to convolution formula 1 minus infinity to infinity, okay, some g1 of say alpha, right, g2 of t minus alpha d alpha. Alpha is a dummy variable, you know, in convolution we have this convolution formula. Now that will be minus infinity to infinity. What is g1 of t? It is m of t. What is g of t? Convolution 1 over pi times t minus alpha, right, d alpha. So it will be 1 over pi m of alpha divided by t minus alpha d alpha. Hence we can write mh of t is 1 over pi integral m of alpha divided by t minus alpha d alpha. This operation, so what we are doing to m of t, so we are dividing this by t minus alpha, integrating it. This operation, when we do it on m of t, is called that we are finding its Hilbert transform. So if you have any function g of t and someone tells you to find its Hilbert transform, so what will you do? 1 over pi minus infinity g of alpha d alpha divided by t minus alpha. This is the Hilbert transform. And what is its significance? That we can get from the Fourier transform of Hilbert transform, mh of t. So you see mh of t, mh of t has Fourier transform m of t, which is equal to, sorry, m plus of omega, m plus of omega, which is given by minus j m of omega sine of signum of omega, j m of omega signum of omega, okay, and which can be written as minus j, sorry, m of omega greater than 0 and j m of omega, sorry, and j m of omega less than 0. Now what is this j and minus j? So if you look at, we can look at it in different way. We can think of filter h of omega with input m of omega and output minus j m of omega signum of omega. If you think of a filter which will find the Hilbert transform, so in frequency domain, what should the filter do? If you feed in the Fourier transform of message, the output should be the Fourier transform of m part of m plus of omega, it is minus j m of omega signum. Then what should be h of omega, right? You know that h of omega will be output by input, right? So this will be minus j m of omega signum of omega divided by m of omega, which is minus j signum of omega, and this we can write as minus j for omega greater than 0 and j for omega less than 0. This can be written as e to the power minus j pi by 2 for omega greater than 0 e to the power j pi by 2 for omega less than 0. So hence it follows that this Hilbert transformer, its in frequency domain, its magnitude is 1 and its phase is minus pi by 2 for omega greater than 0 and it is pi by 2 for omega less than 0. So it means that how to obtain Hilbert transform from a message signal, it tells us that if you change the phase, of every frequency component by pi by 2, right, by pi by 2. So for positive frequencies you change it by minus pi by 2, for negative frequencies you change it for pi by 2, you will get the Hilbert transform. This is the basic idea behind the Hilbert transform. Okay, now after we have found the Hilbert transform, we are now pretty much ready to define the single sideband modulation in time domain. So now if you if you opt for upper sideband on this side, that is m plus of omega minus omega c, and on this side it will be m minus of omega plus omega c. So the single sideband for this will be, I will write phi USB upper sideband in frequency domain omega, m plus of omega minus omega c plus m minus of omega plus omega c. Okay, now in time domain, what will be the function? So I will write phi of USB t, that will be Fourier inverse of this, right? So that will be Fourier inverse of m plus omega minus omega c plus m minus omega plus omega c, right? Now you know this property. If you have g of omega and if you know its Fourier inverse is g of t, what will be the Fourier inverse of g of omega minus omega c? That will be g of t e to the power j omega ct, correct? So Fourier inverse of m plus omega minus omega c will be Fourier inverse of m plus of omega e to the power j omega ct plus Fourier inverse of m minus of omega e to the power minus j omega ct. Now what is the Fourier inverse of m plus of omega? That is definitely mh of that will be m plus of t, right, e to the power j omega ct plus it will be m minus of t e to the power minus j omega ct, correct? Now you know that m plus of t is half m of t plus j mh of t, and e to the power j omega ct is cos omega ct plus j sine omega ct, and m minus of t is half m of t minus j mh of t, and then cos omega ct minus j sine omega ct. After simplifying, several terms will get cancelled out. You will get m of t cos omega ct minus mh of t sine omega ct. This is the time domain representation of single sideband modulation signal when we only transmit upper sidebands. Okay, same way you can do for lower sidebands. But at this point I will this can help us in understanding how can we generate sorry, single sideband signal. See, what you need actually is you need to multiply m of t with cos, then you need to multiply this mh of t with sine. Okay, now the first question is how to generate mh of t, how to generate this Hilbert transform of this. So we just now, after deriving rigorously the Fourier transform of mh of t in terms of that Signum function and all those, the final conclusion we got, if you want to generate mh of t from m of t, what you have to do in frequency domain, you have to shift for positive frequencies. Definitely we are working, we have to shift each and every frequency by minus pi by 2. So you have to use phase shifter. Okay, so if I denote phase shifter by this box minus pi by 2, so this is actually phase shifter. Okay, there are circuits for it, op-amp based. So if to this phase shifter I will put m of t, you will get mh of t. As an example, if I will put here cos omega ct, so what is the minus pi by 2 shift of it? Sine omega ct. Now see how we can generate the DSBSC signal. So m of t, right? So one part of the, if you look at this part, first part of SSB, this is same as DSBSC. So you need something. Sorry. So you need a DSBSC modulator here. DSBSC modulator. You need to feed in the cos omega ct signal here, right? You will get m of t cos omega ct. Now what you need, this was the one part. So now you need mh of t. To get mh of t, you will put here phase shifter. Now you get here mh of t, and you need to multiply. Now you again need a DSBSC modulator here. See, look in the second part. Second part is also DSBSC signal, but instead of m of t there is mh of t. Instead of cos there is sine. Now to get sine from this cos, what will you do? You will again put same phase shifter here. So you will get sine omega ct, and you got here mh of t sine omega ct. Then you put adder here with a plus sign here and minus sign here, and you will get single sideband signal. Phi USB for this case. It is an exercise for you to do phi LSB. That is, if you will take only LSB, lower sidebands, and generate this. See, this is a very elegant method, and you see all of the things we have done. DSBSC modulators we have done. Phase shifter is simply a circuit. You can generate cos using oscillators. You have a simple adder circuit here, and this is the complete design for single sideband modulation. This completes our discussion about single sideband modulation, and I will not discuss any further things, but there are some homeworks, there are some examples in the books. That is a reading assignment for you. You have to study those examples of SSB, very simple, and that will be part of the syllabus also. You have done, I have shown you pretty much theory so that you can understand that. In next class I will start frequency modulation.